I want to start today with a thought experiment. It's something that really jumped out at me from our reading of Leninger this week, and honestly, it's been stuck in my head for days. I'm calling it the time problem.
Ah, yes. The sugar problem.
Sugar problem, exactly. I want you and everyone listening to just picture a simple paper bag of sugar sitting on a kitchen shelf. Just, standard white granulated sucrose. Now, based on everything we've talked about before on thermodynamics, we know the universe basically wants that sugar gone.
Right. That's a fundamental point. If you look at the physics, thermodynamics is very, very clear on this. The breakdown of sucrose into carbon dioxide and water is an exergonic process.
Meaning it releases energy.
A tremendous amount of energy. The equilibrium lies heavily, overwhelmingly, in favor of those products. The sugar should break down. The energy landscape demands it. It wants to roll down that hill.
The laws of physics are all pointing one way, saying go, but, and this is the kicker, if I leave that bag on the shelf, how long does it actually take to spontaneously turn into CO2 and water?
Oh, without any help, just spontaneously. You are looking at years, decades, probably even centuries.
Centuries.
Yeah, for all intents and purposes, to the human eye, or even to a chemist watching it for a lifetime, that bag of sugar is completely stable. It just sits there. Nothing happens.
And yet, if I take a spoonful of that same sugar and eat it, my body breaks it down, extracts that energy, and turns it into exhaust CO2 and water in, what, seconds?
Milliseconds, really. Once it hits the metabolic machinery inside the cell, it's almost instantaneous.
So we have this just massive discrepancy on the shelf, centuries in the cell, seconds. That gap, that difference between what should happen thermodynamically and what actually happens in real time, that is the mystery of life, isn't it?
It is, in a way, the definition of life, biochemically speaking. Life is essentially the ability to accelerate reactions that would otherwise be far too slow to matter.
That's a great way to put it.
If we had to wait for sugar to break down spontaneously, we would starve to death before we got the first calorie. We are engines that run on reactions that shouldn't be happening nearly as fast as they do.
And the things bridging that gap, the things that make it all possible,
are enzymes, the master craftsmen of the cell.
And that is our topic for this deep dive. We are looking at enzymes. And to do this justice, we are synthesizing two absolute Bibles of biochemistry. We've got Leninger's Principles of Biochemistry, specifically the chapter on enzymes, to give us the physics, the deep mechanistic how.
The fundamental principles.
And we've got Harper's Illustrated Biochemistry, a whole section of chapters, really, to give us the clinical context, why this matters to a doctor, how we measure it, and, what happens when these little machines break.
It's a great combination, actually, because Leninger treats the enzyme like a piece of high-precision engineering, something to be admired for its physical perfection.
Right.
And Harper treats the enzyme like a patient's vital sign, something that tells you if things are okay or if they're going terribly wrong.
Now, before we jump in, a quick disclaimer. We are interpreting and synthesizing these texts. We aren't reading them word for word. We really want you to use this deep dive as a kind of map. If you're a student, go back to the books, read the chapters, use our conversation to hang the details on.
Exactly. The goal here is to give you those aha moments so that when you're staring at those complex charts and graphs in the book, they actually mean something tangible. It's about building a framework.
We have a lot of ground to cover. We're going to look at the mechanism, how a protein actually grabs a molecule and forces it to change. We'll look at the speed, the kinetics. Then we absolutely need to talk about regulation, because you can't have these things running full tilt all the time.
No, control is everything. And then we'll get into the toolkit, the metals and vitamins they need to function.
And finally, the pathology. Because when enzymes fail, the result is usually catastrophic disease.
That's where it all comes home to roost, clinically.
So let's start with the numbers. I said seconds versus centuries, but can we quantify that? How much faster is an enzyme than just a random collision in a test tube?
We are talking about doubling or tripling the speed. We aren't even talking about making it 100 times faster. We are talking about rate enhancements by factors of 10 to the 5th, up to 10 to the 17th power.
Or to the 17th.
That is a 1 followed by 17 zeros. It is orders of magnitude faster than even the best synthetic catalysts we can design in industrial chemical plants. It's the difference between a geologic era and a single heartbeat.
That's almost unfathomable. But they aren't just fast. They are incredibly picky. This was the concept of specificity that Harper really emphasizes.
Right, and this is so crucial because the inside of a cell is a nightmare. It is not a clean test tube with just 2 ingredients. It's a crowded, chaotic soup.
Yeah.
You have thousands of different proteins, metabolites, sugars, fats, all bumping into each other constantly. It's absolute molecular chaos.
And the enzyme has to find one specific needle in that massive haystack.
Precisely. It has to ignore 10,000 wrong molecules and bind the one right molecule, its substrate, with absolute precision. And not just the right molecule, but the right shape of that molecule, the right stereoisomer.
This brings us to that three-point attachment model that Harper talks about. I found this fascinating because it explains how enzymes can distinguish between things that look, to us, completely identical.
It explains stereospecificity, the whole concept of the handedness of molecules. Okay, walk us through this. How does it work?
Well, imagine you have a substrate that looks symmetrical. Let's say it's a sphere, like a basketball. To you and me, there's no left or right side of a basketball. It's just a ball. If you pick it up, it doesn't matter how you hold it.
Right. It's uniform. You can spin it any way you want.
But now imagine the enzyme's active site. That's the little pocket where all the work happens. It's not a flat surface. It's a complex 3D shape, like a custom-molded glove or maybe a docking station in a spaceship. Harper describes this model where the enzyme binds the substrate at 3 distinct points.
So like 3 little anchor points. Exactly. Imagine your hand has 3 sticky fingers. As soon as you anchor that basketball at 3 specific points on its surface, it can no longer spin freely. It can't flip over. It is locked into one and only one specific orientation relative to your hand.
Ah, okay. So even though the ball itself was symmetrical when it was floating around, once it's docked, the enzyme knows which side is facing up, which is facing down, which is facing left.
Precisely. And because it's locked in place, the enzyme can then perform chemistry on just one specific side of that molecule. This is why an enzyme can take a neutral, non-chiral molecule like pyruvate and turn it into L-lactate, but never, ever delactate. It creates a specific handedness out of something that didn't have one before.
And why does that matter so much? Why can't our bodies just use D-lactate, or D-amino acids for that matter?
Because the rest of the body, the rest of the entire biological system, is built on a specific standard. Our proteins only use L-amino acids.
Yeah.
Our energy systems rely on D-sugars. If an enzyme started churning out the wrong version, the mirror image, it would be junk.
The next enzyme in the line wouldn't recognize it.
It wouldn't recognize it at all. The entire assembly line would jam. It's like trying to put a left-handed glove on your right hand.
Yeah.
Or trying to screw a bolt with the wrong thread direction.
Yeah.
It just doesn't work. The system grinds to a halt.
So we have mind-boggling speed and we have extreme precision, but I want to really dig into the how. This is the part that I think usually confuses people. How does a clump of amino acids, just a protein, make a chemical reaction happen a quadrillion times faster?
To understand that, we have to go back to the idea of the energy hill, the activation energy. It's symbolized as delta G double dagger or delta G dagger.
Okay, explain the hill.
Picture any reaction as a journey from point A to point B.
Yeah.
Point A is your starting material, the substrate. Point B is the product. Now, even if point B is lower in energy, like that sugar becoming CO2, it's rolling downhill thermodynamically. There's always a mountain pass in the middle you have to cross first.
The barrier.
That peak is called the transition state. It is a fleeting, incredibly unstable, high-energy moment where chemical bonds are half broken and half formed. It's an awkward, unhappy shape for a molecule to be in.
It takes energy to get there.
A massive amount of energy to contort a stable molecule into that state.
So the sugar's sitting on the shelf. The reason it doesn't break down is simply that the individual sugar molecules don't have enough kinetic energy to climb that mountain.
Exactly. At room temperature, they're bouncing around. They have some energy, but they just bounce off the base of that mountain. The barrier is just too high to get over.
So the enzyme's job is to lower the mountain.
Correct. And this is a key myth that Leninger busts right away. Enzymes do not change the start point or the end point. They don't change the overall free energy, the delta G of the reaction.
They don't change the equilibrium.
No. They don't make an unfavorable reaction favorable. You can't cheat the laws of physics.
You still end up at the same place.
Right. The enzyme just creates a tunnel through the mountain. It lowers the activation energy required to get there. It provides an easier path.
Okay, but here's the question that kept nagging me while I was reading this. How? You can't just wish the mountain away. Energy has to come from somewhere. You don't get something for nothing in physics. Where does the energy to lower the barrier come from?
This is the absolute brilliance of Leninger's explanation, and it's the core of everything. The energy comes from binding.
Binding energy. That's the term, delta GB war.
Think about it. When the enzyme grabs onto the substrate, it forms all these tiny, weak, non-covalent connections. We're talking hydrogen bonds, hydrophobic interactions, van der Waals forces.
It's like a whole bunch of tiny magnets clicking into place.
That's a great way to think of it. And every single time one of those magnets clicks, it releases a tiny puff of energy. Snap, snap, snap. The enzyme harnesses all of that released energy, that binding energy, to pay the cost of twisting the molecule into the transition state.
This is what leads us to the stick case metaphor, which I thought was probably the single best visualization in the whole book. Can you walk us through the stick case?
Of course. This is a classic Lehninger thought experiment.
Okay.
Imagine the reaction you want to catalyze is simply breaking a metal stick in half.
Okay, I'm holding a metal stick. I want to snap it. That's my reaction.
Now, imagine you have an enzyme, let's just call it a magnet for this example, that is shaped perfectly like the stick. A long, straight channel. This was the old lock and key idea proposed by Emil Fischer way back in 1894.
The key fits the lock perfectly. Simple, intuitive.
Right. So you put the straight stick into the straight magnet. It clicks right in. It fits perfectly. Now what happens to the stick?
Well, nothing. It's just sitting there.
It's actually worse than nothing. Because it fits so well, the magnet is holding the stick perfectly straight. You've actually stabilized the stick. You've made it harder to break because the enzyme is reinforcing its stable shape. You've fallen into what's called an energy well.
So the lock and key model is actually a terrible design for an enzyme.
For catalysis, yes. It's a great model to explain specificity, why only this key fits this lock, but it actually prevents the reaction. If an enzyme binds the substrate perfectly as it is, the reaction just stops dead.
So what's the better design? What's the modern view?
This is the induced fit model. Imagine a different magnet. This one isn't straight. This magnet is shaped like the stick after you've already started to bend it. The magnet itself is bent. It's curved.
So the active site isn't complementary to the starting material. It's complementary to the broken version.
But the transition state, that halfway point.
Okay.
So when the straight stick enters this curved active site, the magnet grabs the two ends, but the middle doesn't fit right. To get fully into that pocket, to make all those wonderful magnetic connections and release all that binding energy,
The stick has to bend.
the enzyme forces the stick to bend to match its own shape.
The binding energy of the magnet pulling on the ends of the stick is what provides the energy to physically bend the stick towards its breaking point.
Exactly. It puts the substrate under enormous physical and electronic stress. That is the aha moment. The enzyme isn't a passive glove fitting a hand. It's an active machine. It's a torture device that twists and contorts its victim, the substrate.
It distorts it. It brings it right to the brink of reaction so that just a tiny little bit of random thermal energy is enough to push it over the edge. That is the source of the power.
And this is the central principle. The enzyme pays for the transition state by binding to it much, much more tightly than it binds to the original substrate.
It pays for the breaking of the old bond by forming lots of new favorable interactions with the transition state.
Yes, and this single concept, that the enzyme binds the transition state tighter than the substrate, is the absolute foundation of modern pharmacology.
We'll definitely get to the drugs in a minute because that's a huge payoff. But first, I want to shift gears to the how fast. This takes us into section 2 of our outline, enzyme kinetics.
Ah, yes, the language of efficiency.
Harper spends a lot of time on this, and my first question is why? Why do doctors and biochemists care so much about kinetics? It feels a bit like physics envy, all these graphs and equations.
It can feel that way, I know. But kinetics is how we diagnose pathology. In the body, we don't just care if a reaction happens. We care if it's happening fast enough. If an enzyme is too slow, you get a bottleneck.
A traffic jam.
A traffic jam. Toxins can build up behind it, or essential products don't get made downstream. That is disease. Most inborn errors of metabolism, these genetic diseases, are actually kinetic problems. The enzyme protein is there, but it's just too slow to keep up with the demands of life.
And the really weird thing about enzymes, unlike simple chemistry, is that they have a speed limit.
Saturation kinetics, yes.
Right. In a normal chemical reaction like, I don't know, mixing vinegar and baking soda, if I add more vinegar, the reaction goes faster. It's basically a straight line.
Generally, yeah. More reactants, more random collisions, a faster rate.
But with enzymes, that stops working at some point. You hit a wall.
You hit a ceiling because the enzyme is a physical object. It's a worker. It's a machine. Imagine you have a worker on an assembly line wrapping chocolate bars. This is the classic Lucy and Ethel, I love Lucy scenario.
Okay, the chocolate factory. I can picture it.
If you slide one chocolate bar down the conveyor belt to the worker, he wraps it. If you slide 2 per second, he wraps them faster. But if you suddenly dump 1,000 chocolate bars on his table,
He can only move his hands so fast. He's totally overwhelmed.
he is saturated. That maximum speed, that's what we call Vmax, the velocity maximum. At that point, adding more substrate, more chocolate bars, does absolutely nothing to the rate. The line just flatlines. The only way to go faster is to hire more workers, which means synthesizing more enzyme protein.
And this brings us to the most famous and perhaps the most feared terms in all of biochemistry, molars, the Michaelis constant.
Every medical student has nightmares about deriving the Michaelis-Menten equation. But the concept itself is actually incredibly intuitive if you just strip away the calculus.
Let's do exactly that. What is nanomolar's really telling us about our chocolate wrapping worker?
So physically, the definition of nanomolar is the concentration of substrate you need to get the enzyme working at exactly half of its maximum speed.
Okay, half of Vmax. Why is that specific number useful?
Because it's a proxy. It's an inverse measure of affinity. It tells you how good the enzyme is at grabbing its substrate, especially when that substrate is scarce.
So if I have a low OR1, what does that mean?
A low nanomolar means you only need a tiny little pinch of substrate to get the enzyme running at half speed. It implies the enzyme is sticky, it grabs on tight, it has a high affinity for its substrate, it works really well even when the cupboard is bare.
And a high dollar.
A high dollar means the enzyme is a bit aloof. You need to flood the cell with substrate before it really bothers to get to work. It has low affinity. It doesn't bind very tightly.
Now, looking at this from a design perspective, wouldn't you always want a low autoweller? Wouldn't you always want the enzyme to be as efficient and sticky as possible?
You'd think so, but not necessarily. And this is where Harper provides some beautiful physiological context. Think about glucose metabolism in two different organs, the liver and the brain.
Okay. Different jobs, different needs.
Totally different needs.
Yeah.
The brain needs a constant, steady supply of glucose. It cannot run on fat. It's incredibly dependent. So its main enzyme for grabbing glucose, hexokinase, has a tiny dollar.
So it's very sticky, high affinity.
Very sticky. It grabs any glucose molecule it sees, even if your blood sugar is dangerously low. It's greedy. It's designed to ensure the brain always eats first.
A survival mechanism.
It's a critical survival mechanism. But now think about the liver. The liver's job is different. Its job is to store excess glucose as glycogen after a meal. You don't want the liver hoarding sugar when you're starving. You want the liver to leave that sugar for the brain.
Right.
So the liver's version of the enzyme, glucokinase, has a very high Collett-Tower. It pretty much ignores glucose when levels are low or normal.
It lets the glucose float right past on its way to the brain.
Exactly. It only starts working, only wakes up when glucose levels flood the system, like after you've had a big meal. Then, and only then, does it kick into gear and start storing all that excess. Evolution has tuned these biomolarity values to match the specific physiological role of the tissue.
That makes perfect sense. It's not just about raw speed, it's about priority. It's about sharing resources within the larger system of the body.
It's about responsiveness. And in fact, most intracellular enzymes have a collar that's pretty close to the normal concentration of their substrate in the cell. This means they are poised on that steep part of the curve. So if the concentration changes even a little bit, the enzyme's speed changes instantly in response. It's a form of passive autoregulation.
There's one more kinetic number we need to touch on. AKTAT, the turnover number.
If nanomolar is about affinity, TCAT is about raw horsepower. If the enzyme is fully saturated, running at Vmax, how many molecules can one single enzyme molecule convert in 1 second?
What's the range we're talking about here?
It varies wildly. Some are pretty slow. Lysozyme, which is the enzyme in your tears that breaks down bacterial walls, it does about 0.5 reactions per second. It's a slow, deliberate worker.
Half a molecule a second, that's pretty leisurely.
But then you have the absolute monsters. Consider carbonic anhydrase.
That's the one that deals with CO2 in our blood, getting it to the lungs.
Right. One single molecule of carbonic anhydrase can hydrate 600,000 molecules of CO2 every single second.
Wait, say that again? 600,000.
600,000 per second.
That's effectively instantaneous.
It's what we call catalytic perfection. Leninger discusses this in detail. Enzymes like triose phosphate isomerase or carbonic anhydrase work so blindingly fast that the chemical reaction itself isn't the bottleneck anymore.
What is then?
The bottleneck is literally how fast the substrate can swim through the water to randomly collide with the active site. They are limited by the rate of diffusion.
So evolution cannot make them any faster.
Correct. Physics itself won't allow the molecules to move any faster through the medium. They have reached the absolute physical limit of what is possible in this universe.
That is just mind-blowing. We have these literally perfect machines inside of us. But of course, sometimes we need to stop them. We need to interfere. And this is where drugs come in.
Inhibition, Section 3.
Specifically, I want to talk about the imposter, competitive inhibition. This seems like the most straightforward one.
It is the most intuitive type, for sure. It relates directly back to that active site pocket. You have a substrate that's supposed to go into the pocket. A competitive inhibitor is simply another molecule that looks just enough like the real substrate to fit in the pocket, but it's different enough that the enzyme can't actually do the reaction on it.
It takes the seat but doesn't do the work. It just sits there.
Exactly. It's a squatter. It blocks the real substrate from getting in. Harper uses the classic example of succinate dehydrogenase. Its job is to process a molecule called succinate. But if you add a different molecule, malonate.
Which looks a lot like succinate chemically.
It's very similar. It fits into the active site. But the enzyme can't do anything with it. So the enzyme just sits there, clogged up with malonate, completely unable to do its real job.
But the key thing about competitive inhibition is that you can fight back, right? It's not permanent.
Yes. It's a numbers game. It's like musical chairs. If you have one inhibitor and one substrate, it's a 50-50 chance who gets the seat. But if you flood the system with enough real succinate, if you have 1,000 succinate molecules for every one malonate, eventually you will outcompete the inhibitor.
You can push the imposter out of the chair just by having more people trying to sit down?
Precisely. You can overwhelm the inhibitor.
So in terms of those kinetic numbers we talked about, Vmax and chemoliter, what does a competitive inhibitor do to the graph?
Well, because you can eventually win. If you add enough substrate, the Vmax doesn't change. You can still reach your top speed. It just takes a lot more effort, a lot more substrate. But the column, the affinity appears to go up.
It looks like the affinity has gone down.
Right. To the outside observer, it looks like the enzyme is ignoring the substrate, because half the time, the inhibitor is getting in the way. You need a much higher concentration of substrate to reach that half maximum velocity.
Now, I want to connect this all the way back to the stick case and the bent stick. We said earlier that the enzyme binds the transition state much more tightly than the substrate.
Yes, the bent stick. The high-energy, unstable intermediate.
This leads to some of the most powerful and specific drugs we have, the transition state analogs.
This is truly brilliant pharmacology. If you know that an enzyme binds the transition state, the bent stick, 1,000,000 times tighter than the straight stick, then if you can chemically synthesize a stable drug that looks like the bent stick,
a stable molecule that mimics that tortured high-energy transition state,
the enzyme will grab that drug with unbelievable affinity. It will lock onto it and, for all practical purposes, never let go. It binds thousands or millions of times tighter than the natural substrate ever could.
It's like a molecular supermagnet trap.
That's exactly what it is. This is the mechanism behind many of our best antibiotics. Penicillin, for example, mimics the transition state of the reaction that bacteria use to build their cell walls. The bacterial enzyme grabs the penicillin, gets permanently stuck, and the bacterium dies because it can't build its protective wall.
We're essentially hacking the enzyme's own mechanism. We're using its preference for the transition state against it.
We are. It's devious and incredibly effective. Many antiviral drugs, like those for HIV, are also transition state analogs.
That is just... It's so elegant. So we've got the machine, we know how fast it goes, and we know how to jam it with a wrench. But the body doesn't just jam wrenches in randomly. It has a sophisticated control room. This takes us to section 4, regulation.
Regulation is everything. A cell isn't a test tube where you just mix things together and let them run until they're done. A cell has to respond to its environment. It has to respond to a fight or flight signal, or a starvation, or a state of being well fed.
And Harper distinguishes between two main ways to regulate. You can regulate the quantity of the enzyme, or you can regulate its efficiency.
Right. Option A, regulate quantity. This is the slow and steady way. If you need more of a reaction to happen, you just build more factories. You turn on the genes. You go through transcription and translation. You synthesize more enzyme protein.
But that takes time.
Hours, sometimes days. It's great for long-term adaptation like bacteria adapting to a new food source in their environment, or your liver adapting to a consistently high-protein diet, but it's way too slow to save you from a tiger.
Right. You need an instant response. So for the tiger, we need option B.
Regulation of efficiency. You take the workers you already have, and you either whip them to work faster, or you tell them to stop immediately. This happens in seconds or even milliseconds.
And the most elegant mechanism for this is allosteric regulation.
Allosteric literally means other shape or other site.
Action at a distance.
That's a good way to put it. You have the active site where the work happens, but then somewhere else on the protein, sometimes far away, you have a separate regulatory site. If a small modulator molecule binds there, it causes a ripple effect through the protein, a conformational change that reshapes the active site. either opening it up or closing it down.
So it's like a remote control switch on the back of the enzyme.
Precisely. And this leads to very complex and interesting behaviors. Allosteric enzymes don't follow that simple, smooth, hyperbolic curve we talked about earlier. They show a sigmoid curve, an S shape.
Which implies cooperativity. I love this concept. It feels very biological.
Cooperativity is fascinating. It's usually found in enzymes that have multiple subunits, multiple protein chains working together as a team. It's like a flock of birds or a relay team. When the first subunit finds a substrate and binds it, it snaps into a high-activity on shape.
And that snap communicates to the other subunits next to it.
Yes, it physically nudges its neighbors. That change in shape makes them more likely to bind substrate too. So binding the first one makes binding the second one easier, and binding the second makes binding the third even easier, and so on.
So the enzyme is incredibly sensitive to small changes. Once the substrate levels hit a certain threshold, the whole complex can switch from basically off to full blast very, very quickly.
It acts like a digital switch in an analog world. It allows for very sharp threshold responses. Yeah. And this is absolutely vital for one of the most important concepts of metabolism: feedback inhibition.
Okay, walk us through that.
Imagine you have an assembly line making, say, the amino acid serine. You have 5 enzymes in a row, each doing one step. If the cell makes too much serine, you don't want to waste energy and resources making more. So the end product, the serine molecule itself, floats back to the first enzyme in the line.
And it hits the kill switch.
It binds to an allosteric site on enzyme number 1. It changes the enzyme's shape, and the active site closes. The whole assembly line just shuts down instantly. It's like a thermostat. When the room is warm enough, the furnace shuts off. It's a perfect self-regulating loop.
Brilliant. But sometimes you need a harder switch, a toggle switch that stays on or off until you explicitly tell it otherwise. And this is covalent modification.
And phosphorylation is the big one here, the king of covalent modification.
That's adding a phosphate group to the enzyme.
Think of a phosphate group as a massive, negatively charged sticker. It's big and bulky and has 2 negative charges. If you slap that onto a protein, the charge repels other parts of the protein, it twists the structure, it forces a big change in shape. We have enzymes called protein kinases that add these phosphates, and protein phosphatases that rip them off.
And this simple act can turn an enzyme from totally inactive to hyperactive in a split second.
Or vice versa. Some enzymes are turned off by it, some are turned on. It's the primary way hormones signal to the cell. Adrenaline hits a receptor on the outside of the cell, a kinase gets activated on the inside, it phosphorylates a bunch of enzymes, and boom, your whole metabolism has switched to breaking down glycogen for emergency energy.
There is one more type of regulation that I found the most dramatic. You called it the safety pin model in your notes? Zymogens.
This is critical for enzymes that are, for lack of a better word, inherently dangerous.
Dangerous? How can an enzyme be dangerous?
Think about digestion. You have enzymes in your gut like trypsin. Its job is to break down protein from the food you eat. But your cells are made of protein. Your pancreas, where trypsin is made of protein.
Ah, so if you turn trypsin on inside the pancreas.
It will digest the pancreas, it will eat the very organ that made it. And that is essentially what acute pancreatitis is. It is an agonizing and often life-threatening condition where the tissue literally starts to auto-digest.
So how does the body prevent that from happening normally?
It builds the enzyme with a safety lock on it. It synthesizes it as a zymogen, an inactive precursor, in this case called trypsinogen. It has an extra little piece of protein chain that folds over and blocks the active site. It's like a grenade with the pin still in.
And the pin is only pulled where?
In the small intestine. Once it is safely secreted out of the pancreas and into the gut, another enzyme comes along and snips off that little safety chain. The enzyme then snaps open and starts working, but only in the place where it's supposed to.
Harper also mentions this system in blood clotting, which makes perfect sense. You absolutely do not want your blood to start clotting inside your veins unless there's a leak.
Blood clotting is a massive amplifying cascade of zymogens. One zymogen gets activated, it then activates 10 copies of the next zymogen, each of which activates 100 copies of the next. It's a domino effect. This ensures that a massive clot only forms right at the site of injury, where the initial signal starts.
And if you're missing one of those dominoes in the cascade...
That's hemophilia. Harper specifically mentions factor IX deficiency. If you are missing that one zymogen, the signal stops dead in its tracks. You can't form a stable clot. You bleed.
It really highlights how fragile this whole system is. One single missing protein and the entire crucial process fails.
It is an incredibly delicate balance between life and death.
Now, so far, we've talked almost exclusively about the protein part of the enzyme, the amino acids, but often the protein itself isn't enough. They need tools to do their job. This brings us to section 5, the toolkit.
Cofactors and coenzymes, yes.
Why aren't the 20 amino acids enough? That seems like a pretty good variety of chemical groups.
Well, the amino acid side chains are great at acid-base chemistry, shuffling protons around, that sort of thing. But they are pretty terrible at redox chemistry, moving high-energy electrons around. They just aren't chemically versatile enough to handle some of the really tough reactions life requires.
So they hire contractors.
They recruit outside help. This can be inorganic ions, like metals, or complex organic molecules we call coenzymes, which are often derived from the vitamins in our diet. Harper has a great chapter that focuses on these transition metals.
Let's talk about the metals, because we see zinc and iron on our cereal boxes, but I don't think people really realize they are literally essential parts for our cellular engines.
Take zinc. Zinc is a classic Lewis acid.
Okay, break that down for us. What does a Lewis acid do in this context?
It means zinc is electron poor. It has a stable positive charge, usually Zn2 plus Sharpin. It loves to pull on electrons from other molecules. So in an enzyme like carbonic anhydrase, that speed demon we mentioned earlier, the zinc ion sits right in the active site and binds to a water molecule.
And what does it do to that water molecule?
It pulls electron density away from the oxygen in the water. This makes the water molecule extremely nucleophilic. It makes it much more aggressive and reactive. It essentially arms the water molecule to attack the CO2 substrate. Without the zinc, water is too passive to do the job quickly. With the zinc, it's a weapon.
And zinc is safe, right? It's stable.
Zinc is redox inert. It stays at +2. It doesn't swap oxidation states, so it can't generate dangerous radicals. That's why it's also used in purely structural roles, like in zinc fingers, that are critical for holding DNA-binding proteins together. It's like a structural rivet.
Okay, now contrast that with iron and copper.
Iron and copper are the redox warriors. They have multivalency. Iron can switch back and forth from Ep2+ to Ve3+C. Copper can go from Q+ to C2+ Ven.
So they can actually pick up an electron from one place and physically carry it, then pass it to someone else.
Exactly. They are the wires of the electron transport chain in our mitochondria. They conduct the flow of electricity that powers our bodies. But that very reactivity makes them incredibly dangerous.
Because if you drop a live wire in a crowded room,
You start a fire. If you have free iron floating around your cell, it can react with oxygen to create ROS-reactive oxygen species, things like hydroxyl radicals. These are like little sparks that burn holes in DNA, lipids, and other proteins.
so the body has to shield them and has to keep them contained.
You never, ever want free iron or copper in the cell. It's always sequestered, tightly bound inside proteins like ferritin or transferrin. In an enzyme, it's buried deep in the active site, so it can't react with anything except the intended substrate.
This brings us directly to the problem of toxicity. Heavy metals. Lead, mercury, cadmium. Why are they so toxic? Is it just that they're heavy?
No, it's molecular sabotage, it's chemical warfare. Take lead, POB. It sits right below zinc on the periodic table. It has a similar size and charge.
So it's the bad key or the imposter again?
It's a mechanism of displacement. Lead is a better competitor for the binding sites than zinc. So it kicks zinc out of the active site of an enzyme. It sits in the zinc chair. But lead creates a different bond geometry. It can't do the chemistry. It can't polarize the water molecule in the same way.
So the enzyme is dead.
The enzyme is dead. For example, an enzyme involved in making heme for your blood gets shut down by lead. The enzyme is there, but it's non-functional.
And that's why lead poisoning causes anemia. It shuts down the enzymes that build hemoglobin.
That's a major part of it, yes.
And what about mercury?
Mercury has a different but equally nasty trick. It has an incredibly high affinity for sulfur. We call it a sulfhydryl attack. Many critical enzymes have cysteine residues, which have sulfur groups right in their active sites. Mercury binds permanently to that sulfur.
It handcuffs the enzyme.
It gums up the works completely. Harpo mentions the pyruvate dehydrogenase complex, a massive, crucial enzyme complex that allows us to extract energy from carbohydrates. Mercury binds to it and shuts it down cold. It effectively starves your cells of energy, even if there's plenty of sugar around.
It's just amazing that these trace elements, lead, mercury, can take down an organism as big as a human just by targeting these tiny microscopic machines.
It really shows our total and absolute reliance on catalytic efficiency.
Which is the perfect segue to our final section, clinical enzymology. When the machinery fails or when the cell itself breaks, these enzymes end up where they shouldn't be.
Diagnostic enzymology. This is the bread and butter for any physician interpreting lab results.
And the basic rule is enzymes that work inside the cell should stay inside the cell, right?
Correct. The vast majority of metabolic enzymes have no business being out in your blood plasma. If they're there in high concentrations, it means the cell membrane has ruptured, the cell has died and spilled its guts out. It's leaking.
So the blood test is basically a forensic tool looking for the debris from an explosion.
That's a great way to put it. And the type of debris tells you where the explosion happened.
The pattern tells the story.
If I run a blood panel and I see high levels of ALT and AST-alanine aminotransferase and aspartate aminotransferase, I know that those two enzymes are packed in very high concentrations inside liver cells.
So high ALT test means liver damage,
Yeah.
hepatitis, or maybe alcohol damage.
Right. If I see high levels of amylase and lipase,
Those are digestive enzymes, so the pancreas.
acute pancreatitis, the enzymes are leaking out of the damaged pancreas into the blood. And the classic one, if I see a spike in creatine kinase, specifically the CKMB isoform or troponin,
Heart attack, myocardial infarction.
specifically damage to cardiac muscle cells, the enzymes leak out into the blood, and we can actually measure the peak of that enzyme level to see how bad the damage is and roughly when it happened.
But wait, what about enzymes that are in multiple organs? I think the book mentioned LDH, lactate dehydrogenase, is pretty much everywhere. How do you know if it's the heart or the liver that's the problem?
This is where the really clever concept of isozymes becomes incredibly useful.
Yeah.
Isozymes are just slightly different versions of the same enzyme. They do the same reaction, but they have slightly different amino acid sequences, which gives them different physical properties, like a different electrical charge.
So they're the same model of car, but they come in different colors.
Exactly. LDH has 5 different forms made from different combinations of 2 subunits. LDH1 is the form found mostly in the heart. LDH5 is the form found mostly in the liver. By separating these isozymes in the lab, usually using a technique called electrophoresis, we can see the pattern. We can say, oh, the spike is mostly LDH1, so this is almost certainly a heart issue, or it's all LDH5, we need to be looking at the liver.
That is incredibly cool. It's molecular forensics.
It is. We are tracing the chemical fingerprints back to the scene of the crime inside the body.
And finally, we don't just measure them, we use them. We can use enzymes as drugs or as targets for drugs.
Absolutely. We mentioned statins earlier. They target the enzyme HMG-CoA reductase to stop cholesterol synthesis. That's a target. But we also inject actual enzymes as therapeutic agents. The big one is TPA.
Tissue plasminogen activator.
This is a clot buster drug.
Yeah.
If someone is having an ischemic stroke, a clot, blocking an artery in the brain, we can inject TPA into their veins.
What does it do?
It's a zymogen activator. It finds the body's own inactive zymogen, plasminogen, which is stuck in the clot, and it activates it, turning it into plasmin. And plasmin is a powerful enzyme that dissolves the fibrin mesh of the clot. We are essentially jump-starting the body's own enzymatic toolkit to clear the blockage and save the brain tissue from dying.
That is a perfect place to wrap up this deep dive. We've gone from the fundamental physics of the atom all the way to the emergency room.
It's a long journey, but it all connects beautifully.
Let's bring it all back, just for a moment, to that bag of sugar on the shelf.
The impossible sugar.
We started with the impossibility of life. The fact that, without help, the chemical reactions we depend on would take centuries, millennia even.
And we've seen that enzymes are what bridge that impossible gap. They use binding energy to distort reality, to bend and twist molecules into their transition states. They don't break the laws of physics, they just find a loophole. They lower the hill.
But they are not just dumb, brute force catalysts. They are regulated. They are switched on and off by phosphates, by allosteric signals, by having safety pins like zymogens pulled out at just the right time. They are integrated into a vast communication network.
And they rely on this delicate toolkit of metals and vitamins. A single atom of lead in the wrong place can crash the entire system.
It really gives you an almost vertiginous sense of the precision of biology. We are these incredibly complex chemical engines running right on the edge of chaos.
Control chaos, stabilized by these master craftsmen.
So next time you eat a spoonful of sugar, maybe take a moment to appreciate the fact that you aren't going to have to wait 100 years to get the energy from it.
And appreciate the trillions of perfect little machines doing the heavy lifting for you.
So now that we understand the tools, the enzymes that do the work, we need to look at the fuel. How exactly does the cell extract that energy from sugar and other foods and turn it into a usable currency? That is our next deep dive. Bioenergetics.
The laws of thermodynamics in action inside the cell. I can't wait.
Thanks for listening. We'll see you then.